Okay, so again, this video lecture is going to be recorded. So here we are studying projectile motion, and I want to show you this level range formula. It's a useful formula sometimes. What must be true if you're going to use this level range formula? What's the requirement on this? You cannot have any change in the overall elevation change, or elevation of this projectile. So IFF, you guys know what that means? It's a math statement. If and only if there's no elevation change, the ball is kicked from the ground, it lands back on the ground. The range formula can be used to relate the launch angle, launch speed, and the total horizontal range. Now I call that in that lab, I call that the level range formula. So what is the total range for it? The formula states that they're given launch speed. Did you guys see that there were two angles? That would get you to the same range. The formula that I'm going to show you shows that there's two angles that will get you to the same spot. Did you guys discover, anyone come up with the rule that the rule is that those angles are complementary to each other? 30 and 60 go to the same angle. 40 and 50. 25 and what was the test that you guys did? 25 and what was the other one that would get there? 65 should get you to the same spot. Those angles are complementary. That means they would add to 90 degrees. The maximum angle or the maximum range is obtained when the angle is at 45. And so if it's anything less than 45 or anything greater than 45, you would just take the complement and get you to the same value. Now, I'm going to derive this formula for you. And the derivation, it just helps you see how we link the two motions together through a time variable. So this gets a little bit mathy, but this is an honors class, and so we don't shy away from the math at all there. So what I want to do is I want to show you how we derive this formula. Now that formula, R is equal to V naught squared sine of 2 theta over G, is an equation that you can use for any level range problem. I want to derive it. You guys recognize this equation. We've seen it numerous times. So this is our 7th week of the school year. And we've done a lot of 1D kinematics. Now we're doing 2D kinematics, projectile motion as main application. You guys have seen that equation. It's equation number 3 over on the list. Delta y for level range means that this term is 0. So if there's no change in elevation from beginning to end, that term is 0. Instead of v naught y, I'm going to use v naught multiplied by, if this thing is being launched at some angle, can you tell me how to write v naught y in terms of v naught and the angle? V naught times what? The sine of that angle. So v naught sine theta times t. And then minus 1/2 gt squared. Now, you might not think to do this, but I have a sum, or in this case a difference, equal to 0. On the right-hand side, you guys agree that's a difference of two terms. Why might I factor that by pulling out a common t? What would be the value of factoring that? I see that there's a t in each term. Now I'm going to pull out a common t, factor it. What's the value of that, Xavier? Let me write it down, and I'm going to go back to you. I think you might be seeing this. I'm going to pull out that common factor of t. That's just an algebraic step, pulling out a common t. Why might I do that? What would be the value? That's really the question I'm asking. What's the value of doing that step? Yeah. I don't have to take square root, thank you. That's true. One more time.
One of the times it's already equal to 0.
Sure, one of the times has to be equal to 0 for sure. The nice thing about creating a product here is that now I have a product equal to 0. If a product is equal to 0, something tells me that one or both of those terms has to be 0 for that to be true, correct? So the reason we would factor this is because I want to get a product equal to 0. Now this has two solutions. One of those is when t is equal to 0. That's the first case. That's the case right when the launcher comes, or when the device comes out of the launch, right? It's at the ground level. T is equal to 0 is one solution. The other solution is when this is equal to 0. I'm going to ask you to solve this for an expression for t. Take that thing on the right in parentheses. Make it be t is equal to something. I'd like to get that in variable form. Take a moment, see if we can do that. T is either equal to 0 or t is equal to something that will make this term 0. Try it. Now, I didn't say anything as you were doing that because I was hoping you to solve that. You get an expression that t is equal to 2 v naught sine theta over g. Algebraic expression for t. T is either equal to 0 or it's equal to this when the displacement is equal to 0. So when it rises and falls, it's either going to be at 0 seconds or at that value. Now the next thing I'm going to do is I'm going to go over into the blue portion. So I'm going to say delta. Give me blue. I'm going to say delta x is equal to v naught multiplied, or v naught sub x multiplied by the time. And instead of using that time, I'm going to use this time here. So I'm going to take this expression and I'm going to plug it in for this value of t. In your math classes, they call that substitution, right? We're essentially solving a system of two equations. One of those involves the x direction, one of those involves the y direction, and we're linking those together through a time variable. So I'm going to do a substitution here. Instead of delta x, I'm going to write it as r. R has a special meaning here. R, in this case, means range when there's no elevation change. So instead of delta x is r. V naught x, well, if this V naught y was V naught sine theta, this would be V naught multiplied by the cosine of theta. And instead of that value for t, I'm going to write this. Now, can you combine some terms? Can you make that be a little bit simpler? It's not meant to be a math class, but occasionally we have to pull out some mathematics to be able to derive new formulas that will make our life simpler. I see a common v naught, so I'm going to square that. I see a 2 sine theta cosine theta. I'm going to group those. And the reason I might group those is because there's a trig identity that some of you might recognize if you've been through a trig class. You may recognize this trig identity. So r, the horizontal range, is equal to v naught squared multiplied by 2 sine theta cosine theta. And then divide that by g. And I'm going to do one more step for you. This term right here is a trig identity. I can make that 2 sine theta cosine theta into a simpler argument. And that one would be this. So I'm going to replace that one with this. V naught squared multiplied by the sine of twice the angle divided by g. That gives me the horizontal range. Now, I'm guessing some of you, when you were going through and doing this here, did you guys notice that when you doubled the speed, did you guys see that the range that it traveled was 4 times greater? When you tripled the speed, so instead of 10, you went 30. Did you guys see that that went 9 times further? Did you see that equation? See that V naught squared? That very bottom statement where it says the level range formula yet to be given must show that the range is directly proportional to the blank of the launch velocity, the square of the launch velocity. is proportional to the square of that launch velocity. You want to get your egg to go really, really far, make it go faster, right? If you can make it go faster, it's going to be able to travel quite a bit further. Double the speed, it's going to go 4 times further. Okay. Now, do you guys see an inverse proportionality with the acceleration due to gravity? Do you guys see that? G is in the denominator. If I make G twice as big, it makes the range half as big. So this is what we call an inverse proportion. I think a lot of people, if you were struggling at all, it was this bottom one with what that term is. That should be a square. Okay, square of the velocity. Square of the launch velocity. All right. Now, I want to show you how to use that formula on just a couple of examples. Your homework that you guys have for tomorrow involves multiple problems, and kids have told me in the past, I've seen this, kids have struggled with some of those questions. They were challenging. And so the Romeo and Juliet problem, have you guys tried that one? Anyone tried that yet? It's a tough problem. That one's tougher to do. There's some other questions that can only be solved with range formula. And so I put that homework out there for after this lesson to make sure that you have access to it. Okay, soccer ball is kicked at an angle 18 degrees to the horizontal, lands 52 meters away. So there's no elevation change. That tells me I can use that range formula. I'm going to draw a quick little sketch here. And based on that being kicked at 18 degrees, and I don't know that launch speed, I can just simply go out and measure how far that ball travels, and then use that range and that angle to calculate how fast it was kicked. I'll show you that with this formula. We're start with that formula. I'm going to solve that for V naught. So a little bit of algebraic manipulation to get V naught by itself. Anyone else like me, you like to have the thing you're solving for on the left? Okay. Doesn't matter which side you put that on, but usually we like to have things go from left to right. So I'm just rearranging that for V naught squared. Take the square root of both sides. Now I'm going to put in R as 52 meters. So that's how far it traveled when there was no change in the elevation. G, I do not put in negative 9.8 here, folks. I put in a positive 9.8. You might remember when I went through that derivation, I had that minus 1/2 GT squared in there. G itself is a positive 9.8. It's directed downward, but we don't put a negative in there. And then I divide that by the sine of twice that angle. Now, if it's 18 degrees, I would take twice that. And then I just go through and use my calculator for that. I would say that students are going to have trouble if you're coming from a pre-calc or a calculus class where you're in a radian mode. You want to make sure that you're in degree mode when you go through and do this. So 52 times 9.8. Divide that by the sine of twice that angle. So the sine of 36. And I get 866.98. I'm going to take the square root of that now. And when I do that, I get 29.4. And so that would be the speed at which that thing was kicked. Could not answer that question without that range formula. It would be much more difficult to do that. And then the last one, this is our last problem that we can do for today. I would like to get it out there to 65 meters instead of 52. So I'm going to change the angle of that launch. And so I want to solve now the angle that would produce that same range, or that new range. So again, I start with R is equal to V naught squared. Sine of twice the angle. Divide that by G. I'm going to solve this now for theta. Rearrange that equation to get theta by itself. So I'm going to say the sine of 2 theta. Sine of 2 theta is equal to R times G divided by V naught squared. That means 2 theta is the inverse sine of that quantity that we see there. Lifting it up so people in the back can see. I don't remember these numbers. Is it 65 meters? 65 meters. G is a positive 9.8. V naught was that 29.4. And I have to square that. If I forget to square it, I'm going to get a number bigger than 1. I take the inverse sine of it, it says error. So make sure I'm squaring that 29.4. So 65 times 9.8, divide that by 29.4 squared. Numbers less than 1, that's good. I take the inverse sine of that. That gives me that 2 theta is equal to 47.5 degrees. That means theta would be half of that. 23.7 degrees. And then you say, maybe it's not a soccer ball, but it's a punt for football. And that punt is a really shallow punt, 23.7 degrees. You say, I want to get it to the same spot, but I'd like to give some time for the punt team to go down and sort of cover that ball. There's another angle that will get you to that same spot. Your calculator would not give it to you. You would have to then go through and say, my calculator says 23.7, but I'm going to find the other angle by take a complement. So I'm just going to subtract 90 from that, and I get 66.3. So the other angle that would also get me there is a 66.3 degrees. Both of those angles will get there. Okay. Questions for me before I stop this here? Okay, I'm going to stop that video.